Here is an example Thevenin equivalence calculation for an AC circuit. So let's look at the following circuit. We have a 20 volt voltage source that is connected to an inductor and a capacitor and a resistor in series. And again, rather than using values of L and C, we'll just give the reactances. So XL is equal to 1 kiloohm, XC is equal to 3 kiloohms, and the resistance is equal to 2 kiloohms. And we are interested in the Thevenin equivalent circuit with respect to these 2 points. So, how do we figure this out? So first, we can figure out the Thevenin voltage by looking at what the voltage is between points A and B if nothing else is connected to them. So in this case, everything is in series, so this is just a nice voltage divider. So for V Thevenin, we want to look at the voltage between points A and B. And when I say nothing else connected, I mean we still have our circuit, but we're not attaching a load resistance or something to, between points A and B. So how do we figure this out? Like I said, voltage divider. So we have 3 impedances in series. So Z total is equal to ZL plus ZC plus ZR. So ZL is 1 kiloohm in the plus J direction. ZC is 3 kiloohms in the minus J direction. And we have ZR is just 2 kiloohms in the real axis direction. So summing these up, I guess we don't usually do this. Let's just draw this on the complex plane. So our 3 impedances are 1K in the positive direction, 3K in the negative direction. So that's like that. So this is ZL, this is ZC, and this is ZR. So when we add those vectors together, we end up with 2K plus 1 minus 3 is minus 2, so minus 2, or I should put the J first. We try to put the J's first so we can see where they are easier. Minus J 2K. So our total impedance is a complex vector that looks something like that on this diagram. So it's 2 and 2. We can draw a little diagram for it. So we have 2K this way, 2K this way. So the magnitude of Z total is equal to the square root of 2 squared plus 2 squared, which equals 2 root 2, which is approximately, well, it is approximately 2.8, but why didn't I write that down? Oh, I see. Okay, my notes are doing better than me. So we'll leave it as 2 times root 2, and that'll be just fine. And this is, of course, kiloohms. So so hold on to 2 root 2K. We'll use that. Okay, so our voltage divider equation, remember, is Zx over Zr, or sorry, Z total times the voltage applied. So this is going to be Zx, the voltage of component X is just 2 kiloohms, which is real, so that's fine. And we'll put an angle of 0 because now we're dividing these numbers, so we're going to need angles. We're going to need things in polar coordinates, not rectangular coordinates. Divided by Z total, which we just got as 2 plus minus J 2K, but we want it in polar coordinates, so this is 2 root 2 K at an angle of, I should have just pointed it out when I had it drawn on here, an angle of minus 45 degrees. Okay, so dividing Oh yeah, and then multiplied by 20, sorry. So dividing this all out, we get 2k here cancels and 2k here cancels. Trust me, we can do that. And we end up with 20 over root 2, 20 divided by root 2, at an angle of 0 minus 45, which is plus 45 degrees. So 20 over the square root of 2 is 14.1, or, it's the square root of 2 times 10, if that helps. So this is 14.1 volts at an angle of plus 45 degrees, and that's it. This is our Thevenin voltage. So our equivalent circuit, I will start to draw up here. We know it's going to look like this. This is, so our Thevenin voltage source is 14.1 volts at an angle of plus 45 degrees. That's 45 degrees relative to this actual voltage source. So, depending on when you start your stopwatch, this may or may not matter if you're measuring it relative to the actual real life voltage source. Okay, anyway. So we need the Thevenin resistance. So what we do now is we replace our voltage source with a wire. So this circuit becomes this circuit. And now we want the equivalent impedance between these 2 points. Well, this circuit we can also redraw in a way that looks a little better. That is, I'm just going to move these around. So I'm going to take the inductor and capacitor and shove them over on this side just so it hopefully makes more sense to the eye. That these two are in together these two are in series, but that series is in parallel with this resistor. So this is not so bad. We just need to combine. We need to start by combining these. So we have our capacitor impedance, which we already know. That was minus j times 2k. And our inductor impedance, 3k. I'm getting ahead of myself. And our inductor impedance is j times 1k. So the total impedance of these combined, we can replace this with some, unknown effective impedance. Some equivalent impedance to these two combined in series, and it's 1k minus 3k, which is minus 2k. So for this Z equivalent is minus j times 2k. All right, so now we have these two in parallel, and we would like to combine them. I can erase this, yes. Okay, so our resistor is 2k. So we have our resistor in parallel with our equivalent impedance. And so the equation for that is ZR times Z equivalent over ZR plus Z equivalent. So ZR times Z equivalent, we want to have, in the numerator here, we want things in polar coordinates. So this is 2k at an angle of 0 degrees, times Z equivalent is 2k at an angle of minus 90 degrees. Divided by ZR plus Z equivalent is going to be, we can draw this on the diagram, again, 2k plus plus the Z equivalent, which is minus j2k. So we actually end up with a familiar looking impedance in the denominator here. This is 2 root 2 kiloohms at an angle of minus 45 degrees. So we want this in polar coordinates. So 2k times the square root of 2 at an angle of minus 45 degrees. All right, so now we're almost done with this. We have 2k times 2k over 2k. And we also have a square root of 2 in the denominator there. And we have 0 degrees plus minus 90 degrees is minus 90 degrees over minus 45 degrees. So minus 90 minus negative 45 is negative 45. So our angle we end up with is just minus 45. And 2k times 2k, so these are going to cancel. We end up with 2 kiloohms divided by the square root of 2, so that is 1.41 kiloohms with an angle of minus 45. So this is not a resistance, this is an impedance, and it looks like somewhere between, minus 45 degrees is somewhere between a capacitor and a resistor. So I made a mistake up here. I drew this as a resistor, but of course this is a general impedance. I guess I should call that Z Thevenin. And so this value is equal to 1.4K at an angle of minus 45 degrees. So again, not quite an inductor, not quite a resistor, not quite a capacitor, somewhere in between the two. And these are our 2 points A and B. So for any purpose or any measurement that's made at A and B, or anything that's attached to the circuit at A and B, whatever you get in this case is going to be equivalent to whatever you get in this case. All right, cool. So hopefully this is a good example of the Thevenin equivalence, and also a good practice for dealing with these AC circuits, since every little bit counts. There's one last thing I wanted to add about this, and that is the AC circuit version of the maximum power theorem. So I don't know that, I don't remember if I talked about this in lecture before. I think I did not for DC circuits. So the maximum power theorem, for DC circuits said that if I have a circuit that looks like this, and I want to get the most power at A and B with, into some load, my load has to be the same as the Thevenin resistance. So in other words, if I had a circuit that looks like this, with a resistor R Thevenin, the most power I can get out is going to be with a load that is equal to the Thevenin resistance. And this was something that you should have observed in one of the lab assignments, one of the simulation lab assignments. So for AC circuits, the maximum power theorem is almost exactly the same. We get the maximum power transferred to the load, and this load in general is an impedance also. We could connect a capacitor or an inductor or a combination of all those things between A and B. So the maximum power we get transferred to the load is going to be when the magnitude of ZL is equal to the magnitude of the Thevenin impedance. So the magnitudes are the same, and the phase angle of these, the complex angle of those, theta load is equal to minus theta Thevenin. So these are the complex Z angles. So what does this mean? Well, this means that if we have a circuit whose Thevenin equivalent, like in this case, is somewhat capacitive, minus 45 degrees, if we want to get the most power out at A and B, we need a load whose angle is minus 45 degrees, which is plus 45 degrees. We need a load that is inductive between A and B. So in general, inductive circuits like capacitive loads and capacitive circuits like inductive loads, meaning you get the most power out. And this shows up a lot in things like driving motors. So motors, have big coils of wire that have some inductance, and so you can improve the amount of power you get to them by having some capacitance in your circuit because of the max power theorem.